value. And when he found that value, now called Planck's constant, Planck found something more important than an explanation for glowing bodies. He found a new and fundamental truth about nature. Whether by an electrical device or the sun itself, light is absorbed or radiated in discrete bundles of energy. The idea was radical and disturbing, but confirming evidence was on the way. And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge. But when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect. It was Albert Einstein's explanation of the photoelectric effect, and not his theory of relativity, that would eventually win him the Nobel Prize in physics. And in modern terms, here's what he said. An electron in a metal lacks enough energy to escape by an amount called the work function. But if an electron absorbs ultraviolet light that arrives in a bundle having the energy given by Planck's formula, then the electron can gain more than enough energy to escape from the metal. If that's the case, it can come out with kinetic energy equal to h times f minus the work function. This is called Einstein's photoelectric effect equation. It was the perfect solution, and proved as such by Robert A. Millikan in his Chicago laboratory. When he measured the energies of electrons ejected from various metals by different frequencies of light, Millikan verified that while each metal has a different work function, Planck's constant has the same universal value for all of them. But this explanation of the photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A wave has an amplitude and a wavelength, but no beginning or end, and nothing like the definite position of a particle. That remains true if a wave of the same wavelength is added, either in phase or out. But if waves of different wavelengths are added, the resulting shape is altered. And if those wavelengths are close together, and especially if more waves of nearby wavelength are added, the result can be a kind of wave concentrated in a limited region of space. So with a range of wavelengths, and therefore a range of momenta, a wave-like object can be constructed in a fairly definite place. But because it has a range of momenta, it spreads out as it moves along. It isn't really a particle, and it isn't really a wave. What in the world is it?
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here, and I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall, or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
Classical mechanics, but embrace quantum theory as well. For by now, no one can deny the theoretical perfection of the new physics, nor the fact that it actually works.
I have here a demonstration of how the new physics works, which is very elegant, but it's so simple you can easily do it at home yourself with some Polaroid sunglasses. Before I show it to you, let me remind you of how Polaroid works. You remember that light is a wave, but it's a transverse wave. If I have light moving along in this direction, the electric field is actually oscillating perpendicular to that direction, either up and down like that, or sideways in and out of the blackboard, or oblique to that direction. In fact, in an ordinary incandescent light bulb, the light that comes out is oscillating in all possible directions perpendicular to the direction that the light is going in. The direction in which the light is oscillating is called its polarization, and ordinary light is unpolarized. What Polaroid does is to permit through the Polaroid filter only one direction of oscillation of the electromagnetic field. Let me try to illustrate the point to you. Here I have a source of light, and you can see the light on the screen. And this is a piece of Polaroid glass. If I put the Polaroid glass into the beam, the light gets a little bit dimmer. Part of that, of course, is because the glass is dirty, but most of it is because the glass lets through only one polarization of light. I can turn the direction of polarization by turning this handle, but when I do that, you don't see anything happening on the screen because your eye is insensitive to the polarization of light. In order to show you that that light is polarized, I must use a second piece of Polaroid in the beam. Let me do that. I'll put here a second piece of Polaroid. Now the light becomes dimmer again, but this time it really is only because it's a dirty piece of glass. This piece of Polaroid is aligned in the same direction as the first piece, and so everything that gets through the first piece also gets through the second piece. To show you how Polaroid works, I must rotate the direction of the second piece of glass. And when I do it, as you can see, the light gets dimmer and dimmer and dimmer until nothing gets through at all. What's happening now is that only light that's polarized up and down is getting through the first piece of glass. The second piece of glass will transmit only light that's polarized horizontally, and there isn't any of that. And so nothing gets through, and the screen is blank. What's a little more difficult to understand is what happens when the second one is oblique, like that. Then part of the light gets through. Because the light comes in, it's waving up and down. This one allows light that's waving this way, but each vector has a component along that direction, and that part of the vector, that part of the wave gets through. So that's the explanation of how Polaroid works, and it's very easy to understand so long as we believe that light is a wave. But remember, light is also a particle, and there must be a particle explanation of how this occurs as well. So let me tell you how that works. The problem here is that I can't say that part of the light gets through the second filter when it's oblique, because a particle either gets through or it doesn't. Every photon either comes through or doesn't get through. So here is the way it works. The photons come along, the light particles come along to the first filter. And the first filter says, listen guys, every one of you is either polarized up and down or sideways. Nothing else is permitted. But you're polarized up and down or sideways with some probability. Half of you are up and down, and half of you are sideways. Then the light gets through the first one, the ones that are up and down, and all the sideways photons get stopped. Now between the two, I've only got photons that are polarized up and down. This one, as long as it's in the sideways direction like this, says, You guys are all up and down. I only permit sideways photons through, so nothing gets through. If I turn it up like this, it says, you guys are all up and down, and I let up and down photons through, so they all get through, and you can see the light on the screen. The tricky part happens when I turn it in the oblique direction like that. Because now this says, listen guys, you thought you were all up and down, but that's not true. Everybody has got to be either oblique this way or oblique that way with some probability. And you thought you were up and down only because half of you are this way and half of you are that way. And he lets through those that are polarized this way. That's the particle explanation of Polaroid. Now I'd like to try one more experiment with you. I'm going to turn this Polaroid so that nothing gets through. And then I'm going to take this Polaroid here, a third piece, and put it at an oblique angle to the other two. This one is up and down, this one is horizontal, and this one is oblique. And I'm going to put the oblique Polaroid between the other two. Now what will happen is the following. Only up and down photons get through the first one. They get to the oblique one, and he says, you're not up and down. You have a 50% probability of being oblique this way and getting through, 50% probability of being oblique that way and not getting through. The ones that are this way get through, and they get to this guy. And this guy says, you guys all think that you're oblique this way, but you aren't. Each one of you has a 50% probability of being horizontal and getting through, and each one has a 50% probability of being vertical and not getting through. So the horizontal ones get through. But that means that the beam of light will reappear on the screen. You really believe that's going to happen? A scientist has to be prepared to make predictions. So let's see what your predictions are. How many of you think the light beam is going to reappear on the screen? Raise your hands. Let me see. How many think that it won't reappear on the screen? Okay? I've got all your names written down. Let's try the experiment. I'm going to take this and put it back into the light beam, and I claim the light will reappear on the screen. You ready? And there it is. And that is the essence